So, ladies and gentlemen, today we are going to talk about what happens in the so-called geometry processing stage in the rasterization-based rendering pipeline. So, as I have said last time, so in this geometry processing stage, we work on the vertices that give the shape of our geometric object. And we have also said already that there is a vertex shader, so a program which we can write, which tells what kind of operations are then performed on the vertices. So what goes into the geometry processing stage and then into the vertex shader is the per vertex attributes, which are in particular the coordinates of the vertices. We will see later on why we now have 4 different components, and one of these components is a 1, the last one, the so-called homogeneous one. So then we can specify colors. We can specify red, green, and blue components, giving the final color of every vertex. And in addition, and we'll use this later in this lecture, we can specify an alpha value, and this alpha value indicates the transparency or opacity of a certain mesh structure. Then we can also issue the normal vectors for each vertex, and in addition texture coordinates. These can be 2-dimensional coordinates if we map into a 2-dimensional texture map, or as we have also said in one of the previous lectures, these texture coordinates can also reference into a 3-dimensional texture map. And then in addition, in this geometry processing stage, we specify a set of so-called transformation matrices. They are typically issued via the application program, and by means of these transformation matrices, you then perform certain geometric operations on the vertices. And here we see how these transformation matrices look in general. And we will now go into the details of the different components of these matrices and see what kind of operations or what kind of transformations can be applied by using them. So the basic per vertex operations we perform in the geometry processing stage are the coordinate and the normal transformations. So the vertex coordinates need to be transformed so that, for instance, you position the object at a certain location, or you want to the object make larger or smaller. Maybe you want to orientate it so that you can look at the object from a different angle. In addition, if you do that, you also have to think about how to transform the normal vectors, because you can already imagine that if I transform a geometric object, and then after the transformation, of course, the normal vectors should still be orthogonal to the local tangent planes at each vertex. And we have to take care of this by transforming the normal vectors accordingly with respect to the performed coordinate transformations. Then comes the perspective projection. So we will also go into the details of this particular kind of transformation, which essentially brings the vertices from 3D space now into the 2-dimensional image space, so that then the rasterizer can compute the coverage of the pixels by the projected triangles. There's also other operations, in particular being performed on the triangles, and they can optionally be carried out in the geometry shader stage, the shader stage which comes after the vertex shader stage. And let me just emphasize 2 specific operations here which are useful and which are often carried out in this geometry shader stage. The first of them is what we call front or back face culling. So what does this mean? Well, let me just illustrate this. Let us assume that we have 2 triangles like that. So here we have the normal vectors for the 2 triangles. And now let us assume that you're looking from here onto these triangles. So that indicates the view direction. And now you see that one of the triangles, this one here, is what we call front facing, meaning that if you compute the angle between the normal vector and the vector towards the viewer, or the inverse view direction vector here, then this angle here is less than 90 degrees. And if you do the same for the normal vector here, then you see that this angle here is larger than 90 degrees. And so this classifies triangles as being front-facing or back-facing. And one of the things, for instance, you can do in order to reduce the number of triangles that have to be rendered, you just discard all triangles that are back-facing with respect to the view direction. That is what we call front and back face culling. And another operation is what we call clipping. That essentially means that you remove triangles that are outside the visible space. So as we will see, what you typically do is you specify a so-called view frustum. And we will look at this frustum in more detail later on. And this frustum essentially determines the portion of the three-dimensional space that which will be seen, which will be rendered. And now you can, let's say which will be seen. And now if you have a triangle, for instance, which is outside that visible space, then if you can quickly determine that it is outside, you can also disclude it from being rendered, or exclude it from being rendered. You can just say, and that is what clipping does, whenever it can be decided that an entire primitive, an entire triangle is outside the portion of the 3D space that is going to be rendered, then we just clip it away. So we remove it so that then these triangles do not have to be going further through the rasterization-based rendering pipeline. And the result of that geometry processing stage is then the projected triangle vertices in homogeneous coordinates, whatever this is. We will look at this later on, with their associated attributes. So here the vertices are projected, and the result of this stage are then the projected triangle vertices. And the attributes mostly remain unchanged. Texture coordinates remain unchanged, colors remain unchanged, but as we have said already, the normal vectors, they have to be transformed accordingly. So, when looking at the transformations that have to be applied in the geometry processing stage, we typically use that so-called camera analogy, which says, okay, what do we do in the real world if we want to take an image of an object in that real world? And first of all, we do what we call modeling. So we place the object at some location, we orient it so that we look at the object from the right side, so to say. We might also, if it is possible, make the object a little smaller or a little larger, which is not so easy, of course, if you have a real-world model. But if we could, we would just arrange the model with respect to its orientation and size so that it fits well, so to say, the environment, and then gives a nice image of this. And this is what we call the modeling transformation. Then we have the so-called viewing transformation. Here we position and orient the camera. So we place the camera somewhere and we let the camera look under a certain perspective at the object. Then comes the projection. So in the real world, that would mean that we adjust the camera lens. And then finally, we take the photograph, and this means that we then bring, so to say, the image to the 2D screen, whatever this screen looks like. In the real world, of course, it looks different than if we simulate that viewport transformation by means of a computer, as we will see later on. So now here are the different transformations we then use according to the 4 transformation stages or transformation types we have discussed here. So first of all, the vertices go into the geometry processing stage. The vertices here we assume are given in object space, so they come in R3 in coordinates in the R3 in the object space in which the object now has been given. Then comes the first transformation, which is called the model view transformation. So the model view transformation essentially combines the modeling transformation and the viewing transformation. That's the reason why this transformation is called the model view transformation, realized via the model view matrix. We say that this model view transformation transforms the vertices from object space to what we now call the view space. Now, once the vertices are in view space, we apply the projection transformation via the projection matrix. So here we now project the vertices from 3D space. The view space is still a 3D space into a 2D, let's call it screen space. Now, this projection transformation then brings the vertices from view space to what we call the clip space. It's called the clip space because in this particular space, certain clipping operations are performed. Yeah, finally then comes first what we call a perspective division. That is difficult to understand at that time because we didn't really talk about how a perspective is real, a perspective transformation is realized, and we didn't talk in particular about the extension of our three-dimensional coordinates about a fourth so-called homogeneous component. We will look at this in a second. But what comes now at this point in the pipeline is a division through the fourth component, wherever it comes from, which essentially performs a perspective division. And after that, we are then in what we call the normalized device space. That is a two-dimensional space, essentially, with all the coordinates between the coordinates of the visible parts of the scene between -1 and 1. And then comes the final viewport transformation, which essentially takes these normalized device space coordinates and projects them into, let's call it pixel coordinates, or just coordinates in the so-called window space or viewport space. So that is the final transformation here, going from normalized device space coordinates into the pixel coordinates. Then you can imagine that this is important for the rasterizer, because the rasterizer now really needs to know where the projected vertices come to lie in the pixel raster, because by means of these coordinates, then the coverage of the triangles in the pixel raster can be computed. Yeah, in green, we have here the operations that are performed in the vertex shader state. So meaning that you, by means of a shader program, have to take care that the appropriate transformations are applied to the vertices. And here in orange, we have what is done in the rasterizer stage, meaning that you can not really control in detail what is going to happen there, but these transformations are automatically realized by the rasterizer in order to, at the very end, so to say, compute the coverage in the pixel raster. Okay, so now let us look in a little bit more detail on the specific transformations we apply. And first of all, and most importantly probably, we perform these transformations in what we call homogeneous coordinates. And what does it mean? Well, for the, let's say, the basic transformations which come immediately into our minds, like a rotation, like a shear, like a scaling, we could live with a 3x3 matrix. No? In this 3x3 matrix, we can essentially encode all linear transformations. We will look into the differences between linear transformations and affine transformations later on. So for now, let us just say that many of the basic operations are linear operations, and they could immediately encode it in a 3x3 transformation matrix. However, we see that there's a particular nonlinear transformation, which is a translation. Translation in R3, or just a shift from a movement, let's say, from one position to another position. And such an operation cannot be encoded into a 3x3 transformation matrix. And therefore, we just extend the transformation matrix from 3x3 to 4x4, so that then in these three components we can encode the translation. And in addition, what we do, we also use that homogeneous part here. As we will see, these entries here, the first 3 entries in the last row of the 4x4 transformation matrix, will be used in order to realize a projection. And here in this component, we essentially encode at the beginning, so when the elements are going to be transformed by a transformation matrix, we encode in this component here whether we have a vertex, so a location in 3D space, or a direction that is going to be transformed. Yeah, and in order to now let elements being transformed by such a 4x4 transformation matrix, we extend each element about a so-called homogeneous coordinate. And for a vertex, as we will see, that homogeneous coordinate will be 1, and for a directional quantity, it will be 0. So, objects are typically modeled in a local object coordinate space. That is, for instance, space as you see here. For instance, if you model a sphere, then you would maybe say, okay, first of all the sphere vertices will be located in the unit cube ranging from 0 to 1 in each of the 3 spatial, along the 3 spatial coordinate axes. But of course, then you want to place that object in the so-called object coordinate space together with other objects. And then you, for instance, want to move the circle that you have modeled in the local, so you want to bring it in a global world space coordinate. Sorry, it is modeled in the local object coordinate space, and then you want to bring it together with other objects which are also modeled in a local object coordinate space into the global world space. For instance, now the sphere you have modeled should be moved to some position here, and maybe you want to make it a little smaller or a little larger, meaning that you have to somehow transform from the local object coordinates into the global world space coordinate system. And in addition, of course, you very often you don't want to only use one single object, like for instance in the example we see here, where we have a model of a, what is it? It's a dog or whatever, and this dog now should be rendered many times at different locations and at different orientations. And of course, you don't want to now model that particular object as many times as it is seen in that image here, but rather you want to model the object only once. And then you want to apply different transformations onto that one model so that it then appears multiple times at different locations and different orientations. And what we render then is a portion of the global world coordinate. That is the world coordinate system we have here, and all the objects which are initially modeled in their local object coordinate system now have to be brought into that world space coordinate system. So the objects are placed in this space and oriented in that space, and in order to do that, we use the modeling transformation. And this then brings us to what a transformation is, because now we want to look in detail at some specific transformations which are very often used. So in general, we can say such a transformation takes points, x, y, z coordinates in 3D space, and maps these points, which are given in a certain coordinate system, to points in the same coordinate system. Just changes the position, and by changing this position and also by changing the position of points relative to each other, now we can then apply certain transformations like scalings on the triangles making up our geometric shapes. Now in particular, we will consider here transformations of the following form. So we say we have the initial vertex coordinates, and then we compute the transformed coordinates for the x component x prime, for the y component y prime, for the z component z prime. And you see here the type of transformations we apply. So these a, b, c, d until l, these are just constants. And yeah, we now select these constants so that the appropriate transformation of the initial coordinates is performed. Yeah, and by doing so, now we take points x, y, z in Cartesian coordinates and map them to points x prime, y prime, and z prime, also in Cartesian coordinates. Yeah, and then the first thing which we can do is we can just rewrite this set of equations. No, we essentially have three equations telling us how the x prime, the y prime, and the z prime component should be computed by using the transformation on the x, y, and z coordinates of the input vertex. Now, and we see immediately that we can write that transformation here in the following way. We can say that p prime, which is the transformed vertex coordinate comprised of x prime, y prime, and z prime, is equal to, and then comes here a transformation matrix M, which is just comprised of A, B, and C in the first row, then E, F, and G in the second row, and I, J, and K in the third row, times the input vertex coordinate x, y, z, plus, and then comes that last part here, which is just, so to say, the translation components, which shift the vertices in 3D space, and they are just given here as a separate vector. Now, and you see, we now have a 3x3 transformation matrix, and we see immediately that this final translation here, or the translation components, they cannot be included in the 3x3 transformation matrix. And therefore, we now use what we call extended or homogeneous coordinates, meaning that all the coordinates are just extended by a fourth component, the so-called homogeneous coordinate. And we do so in order to capture translations and all the other transformations we have looked at in one transformation matrix. So what we see here is the standard formulation as we have introduced it before, and what we can now say by extending the transformation matrix from 3x3 to 4x4, and also extending the input vertex by an additional homogeneous coordinate, and then also getting an homogeneous coordinate for the output vertex. Then we can now write the whole transformation by just using one single transformation matrix M. And this then is called the homogeneous formulation. So now, let us just look at the specific meaning of this fourth homogeneous coordinate here for vertices and for directions. Now, so far we have mainly talked about how to transform vertices, and so if we have a vertex, then we have said that we want to realize a translation, giving by the values in these three components here, letting this translation being executed on a given vertex. And in order to do so, we just specify for every vertex a 1 in the fourth extended homogeneous coordinate. And by doing so, we see immediately that if we now multiply the 4x4 matrix here with this vertex in extended coordinates, then we always add so the d times 1 to the x prime coordinate, and the h times 1 to the y prime coordinate, and the l times 1 to the z prime coordinate, meaning that this transformation then does exactly what we want to do. So it just applies the translation components to the vertex. So that is the image which we have here. So you have a point in space, or a location in space here in 2D space, and you now want to bring that location here to some other location. You want to transform the vertex P to some transformed vertex P prime via a translation. And now you can imagine what happens if the element which you specify and which should be transformed is not a vertex coordinate, but it's a direction. Now imagine what should happen with a direction. You have a direction vector here, and now imagine you want to translate a direction vector. Now, it is clear that under a translation, a direction should not change. The direction stays the same. and meaning that if you now let a directional quantity being multiplied by such a 4x4 transformation matrix, where you have in these three components here the translational components, then these components should have no effect on a directional quantity. And in order to enforce this, whenever you specify a directional quantity, you just have a 0 in the fourth homogeneous component, because now if you multiply that 4x4 matrix with the 4-component vector, then these final translational components do not have an effect. And after the transformation, you obtain a 0 in here, again indicating that this is a directional quantity. Now, compared to a 1, which you have here in the final result when you transform a point location.